Yes, students, in this session we will discuss about lead compensator designing problem 1. See, the question is design a phase lead compensator for the system shown in figures. Satisfy the following specifications, that is phase margin of the system is greater than or equal to 45 degree. Steady state error for a unit ramp input is less than 1 by 15. The gain crossover frequency of the system must be less than 7.5 radian per second. So, you are asked to find out a designing of a lead compensator, and that lead compensator should satisfy the condition, that is phase margin should be greater than or equal to 45 and steady state error should be less than or equal to 1 by 15. Gain crossover frequency should be 7.5. It should less than 7.5 radian per second. That are the three requirements. So the the closed loop system is shown here, and it has got an open loop transfer function k by s into s plus 1, and here the feedback is 1. So first of all, we have gone through the design procedure for lead compensator in the previous video, and we need all the steps for that procedure, and we have to start solving this problem by taking this function, that is k by s into s plus 1. Here we have to find out the value of k which satisfies the condition steady state error for the unit ramp input less than or equal to 1 by 15. So first step is determination of k. And here the steady state error is less than 1 by 15, that is for the ramp input function, and we know that in the case of a ramp input function, steady state error will have the equation ESS will be equal to 1 by kV, and that will be equal to 1 by 15. So kV will be equal to 15. And we also know that in the case of a second order system, having kV has the equation kV equal to limit s tends to 0 s into g of s into h of s. So here h of s is 1. So we can write kV as kV will be equal to limit s tends to 0 s into g of s value is k by s into s plus 1. So that will give the value is equal to k. Since s is equal to 0, this s and s cancelled out, s is equal to 0. So kV will be equal to k. So we have got the value of k as kV, which is equal to, what is its value? 15. kV will be equal to 15. So k will be equal to 15. So we can write the g of s value as k by s into s plus 1, which is equal to 15 divided by s into s plus 1. Instead of k, we are substituting 15. So now we have the open loop function like this. So for designing the lead compensator, first of all we have to draw the Bode plot corresponding to this open loop transfer function. For that we have to substitute s is equal to j omega value. So s will be equal to j omega. So this function will become g of j omega will be equal to 15 by j omega into 1 plus j omega. From this function we can find out the magnitude. We can draw the Bode plot, that is it includes a magnitude plot and a phase plot, which we will draw on the semi-logarithmic graph sheet. So first step is we have to draw the magnitude plot. For drawing the magnitude plot, we have to make a table that includes different terms. First term is 15 by j omega and the second term is 15 by 1 plus j omega. Here you have to arrange these terms in the table 1 in the increasing order of their corner frequency. Here corner frequency for 15 by 1, there is no corner frequency corresponding to 15 by j omega, and the corner frequency corresponding to 15 by 1 plus j omega is, it is equal to 1, because it is in the form of 1 plus st, t will here be 1. So you can find that omega c1, that is first corner frequency, is equal to 1 radian per second. There is no other terms. So here is only one corner frequency, that is omega c1 equal to 1. And by the design procedure, we have to select a corner frequency that is less than the lowest corner frequency, and also select a corner frequency which is higher than the highest corner frequency. Since here there is only one corner frequency, the lowest corner frequency selected should be less than 1 and highest corner frequency selected to be greater than 1. Okay. So let us see the table. First term is, we know that there is only one corner frequency, so we can arrange the terms in the increasing order of their corner frequency as 15 by j omega d and 1 by 1 plus j omega, and corner frequency here there is no corner frequency and here it is equal to 1. Okay. So this term in this form, the corresponding slope will be minus 20 dB, and for this the corresponding slope will be minus 20 dB. That we have discussed in the case of Bode plot. So this is minus 20 dB. And we are selecting an omega L and omega H value. Omega L will be less than omega C1. Here we are selecting it as 0.1 radian per second. Similarly, omega H should be greater than omega C1. That is, we are selecting it as any value you can select. You can either select a 5 or 10, whatever it is. And here it is selecting as 10 radian per second. So now we have 0.1 radian per second, 1 radian per second and 10 radian per second as omega values. So we have, in order to plot the magnitude plot, we have to find out the value of the gain corresponding to these omega values. So the gain has the equation A equal to modulus of G of j omega in decibels. And for that, for the first two, we have to select taking this as the equation, that is 15 by j omega. So at omega equal to omega L, that is equal to 0.1 radian per second, A will be equal to 20 log 15 by j omega. Here we are taking modulus value, so it will be equal to 20 log 15 by 0.1. Instead of omega, we are substituting 0.1. So that will give approximately a gain value 44 dB. Next we will take next corner frequency omega equal to omega C1, that is 1 radian per second. For finding the gain, we are using the same equation. This 20 log 15 by j omega, that will approximately equal to 24 decibel. Next we are taking highest corner frequency, that is equal to 10 radian per second. For that the gain will be A equal to, we have an equation, that is slope from this omega C1 to omega H into log omega H by omega C1 plus gain at this omega equal to omega C1. So for finding the slope from omega C1 to omega H, we have to go to the table. See here, you can see that this is the slope. So to find the change in slope, here the change in slope at this point will be obtained by minus 20 plus minus 20, that is equal to minus 40 dB. So here we can substitute slope from omega C1 to omega H will be equal to minus 40 into log omega H by omega C1 is, omega H is 10 and omega C1 is 1, plus gain at omega equal to omega C1. What is the value of gain at omega equal to omega C1? That is 24. That 24 is written here. So that will be equal to minus 16 dB. So at various points of omega, we will get different values of gain. So now we can plot the magnitude plot. You can mark the points as at A, B and C. So you can draw the graph like this. See, at the point, for that in the semi-logarithmic graph, you have to mark the points for various omega values. Here you have different values as 0.1, 1, 10. And corresponding gain values are 44, 24 and is minus 16. So gain has a positive and a negative values. So it is marked in the y-axis. So we have to take a 0 axis and there should be some positive values and negative values. And omega, that is angular frequency, is marked, or it is a logarithmic, it indicates a logarithmic value that is marked on the x-axis. And so here we have to take a 0.1, 1 and 10 values. You can use any scale. So here it is 0.1, 1 is marked here. See here it is marked as at the 0.1. And for our need, you can change the scale from this point. See, from this point you can change the scale, but here there is no need. If omega has got the different large values, you have to change the scale. Then only you can include that point in this graph. Here there is only different values such as 0.1, 1 and 10. So you can include it in the same graph by using the same scale. That is why here 0.1, 1 and 10 taken. See, if you are using, suppose if there is omega values as 600, then you have to change the scale at different points. So if you are taking point 1 here, you can take 1 at this point and you can change to the other scale as 100 here, like that. You can change the scale at this point, okay. So here there is no need for changing the scale because here only smaller values are here. So you can take point 1 if you are taking at this point 1. You can see here that 1, 2, 3, 4 points are marked here. It is for identifying the logarithmic scale up to this point. From 1 to 2, the scale is same. From 2 to 3, the scale is same. The changing point is 2 and 3. That is what is marked here. And here you are taking at 1, you are taking the value as 0.1, and then you are taking the value of 1 as at this point, okay. You can see 1 is marked here. Next, the value is 10, so you can use the scale up to this value. That means each column has got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is, it is increasing in this same manner. Next value, if there is no need to find the next value now because your magnitude plot is up to 10 radian per second. So if there is any other value, you can mark the scale. See, here it is marked as 100. If it is needed, you can mark that value. So next scale, you can see here it is 10. Next it is taken that up to this point it is 100. That means the one division has got 10, 20, 30, 40, 50, like that. So you can change the scale at this point, okay. So that is possible in the case of semi-logarithmic graph, okay. So now you can mark the points. First, for point 1, the magnitude is 44 dB. Similarly, you have to mark the scale on the y-axis. Here it is taken as, usually we are drawing the magnitude plot on the upper side of this logarithmic graph, and the phase plot is drawn on the lower side of the logarithmic graph. So you can choose an appropriate division here. You know, here the positive value goes to maximum of 44 dB. So you can use a scale. See, up to 50 you can mark here. See, 0 is taken somewhere here. That means you have to mark positive values up to 44. That is why it is taken, because you have to use the lower portions for drawing the phase plot also. That is why take the 0, take the magnitude readings at the upper side. So 0 is here. Then you can go linear scale for the y-axis division, that is 10, 20, 30, 40 and 50. Up to that reading you need that readings only, because maximum reading is 44. So next, at the lower side you need, see here the negative values are only minus 16. So you can mark minus 10, minus 20 alone. No need to mark other points, okay. So first of all, near to point 1, the value is 44 dB. That you can easily mark. Point 1, the dB is 44 dB value. Next reading is 1. For 1 radian per second, it is 24 dB. For 1 radian per second, you can go like this from 1 to that is 24 dB. That is, this is it is in between, somewhere between 20 and 30. That is marked as B. That is 24. Next, for 10 radian per second, it is minus 16. That is 10 radian is here. For 10 radian, it is minus 16. So it is in between, somewhere between 10 and 20. That is, it is marked as a C. So we can join this curve, that is A to B, B to C. So that is our magnitude plot without a compensation. That is why here it is written as magnitude plot of uncompensated system. You can mark the slope values, that is minus 20 dB and minus 40 dB, okay. That is obtained from the table. Here it is minus 20 dB and next is it is minus 40 dB, okay. Next, see, now you got the magnitude plot. Next you can draw the phase plot. For drawing the phase plot, you have to take the phase of the transfer function. See, here your transfer function is this one, and how will you get the phase? Here for the j omega, phase is 90 degrees. Since it is in the denominator, so the phase will be minus 90. Similarly, for 1 plus j omega, the phase is tan inverse omega. Since it is in the denominator side, so the phase will be minus tan inverse omega. So together you can write the total phase will be angle of g of j omega, that is equal to minus 10 degree minus tan inverse omega. So the phase angle of g of j omega can be calculated by putting different values of omega. So you will get different phases. Here you know that you have different values of omega, as omega is equal to 0.1, 1, 10, and you can take other values of omega for getting the continuity or for getting an exact shape for the phase plot. So you can take 0.5, 0.6 or whatever value you can take. You can see in between 1 and 10 you can take 5, 6, 7 or whatever values. That depends upon you. And here it is taken as omega 0.1, 0.5, 1, 2, 5, 10. Different values are taken. That is 0.1, 1 and 10 are in the magnitude plot. So that points are keeping here, and other values you can take as your wish. Okay. So you are simply substituting these omega values in this equation so that you will get this phase value phi. So you will get different values, minus 96, minus 117, like that. These values you will get and you can make the calculation in the calculator. So here you can notice that here the phase values are negative. So for writing the for plotting the phase plot, you have to mark negative phase angles at the graph on the graph sheet, and you can use suitable scales. You know that y-axis the scale is linear. So here starting from minus 96, so you can start the reading from minus 90, minus 100, minus 110, 120, like that. You can continue up to minus 170. If there is no space for drawing the phase plot, you can use different scale such as minus 90, minus 110, minus 130, like that. Okay. Let us see the phase plot here. You can, if you are starting the 0 axis here, see this is the 0 axis for the magnitude plot, and you can utilize the same axis for the phase plot also, but the y-axis is different. You can if you are taking different 0 axis, you can go like that. Okay. Here for saving the space, 0 axis is taken the same axis. So starting from there, minus 90, minus 100, minus 110, minus 120, like that, it goes up to minus 180. And for different omega values, first omega value is 0.1. So first omega value is 0.1. See here, this is omega 0.1 and corresponding phase is minus 96. So mark that point, minus 90. This is the point. See here, it starts from 90. So minus 96 will be here. So mark that point. You can mark it as ABC already used. You can use D, E, F, G notation like that. So that point is marked, and here we are naming each point in order to avoid the confusion. Okay. And next for 0.5 phase is minus 117. 0.5, see here it is marked as 1. So 0.5 will be, since it is the entire division has a value 1, that means from here to here it is 1 value. That means 0.5 will be locating here. See. This is 0.1, 0.2, 0.3, 0.4, 0.5, like that. 0.5 will be. See, this is 0.1, 0.2 will be here, 0.3, 0.4, 0.5 will be this point. The 0.5 you can mark here. See, 0.5 is corresponding to fifth one. Okay, 0.5 will be here, and you can, what is the value of magnitude? Magnitude is minus 117. So going from 0.5, see from here 0.5 starts. Magnitude value is minus 117. So minus 117, this is minus 120. So it is upper to this minus 120. So the point will be here. Okay. So you can join these two one. And the next point is 1. See, 1 is exactly marked here. Here is the 1. So this is corresponding to this point. So 1. What is the angle? That is minus 135. Angle minus 135 is somewhere between 130 and 140. So going like this, 1 will be here. So 135, you can mark the 135 point here because it corresponds to 1. Okay. This is 135. Okay. Next, similarly you can, for 2 it is minus 153. For 2 is 1 is here, and next division goes to 10. That is, you can see 1 is here and this is 10. So each one, this is 20. Sorry, this is 1. Since it has got a total value of 10, so each one is, if it is 1, it will be 2, 3, 4, 5, 6, like that. So for 2, this will be the value. For 2, it is minus 157. So it is in above 150. So that will be the point. So next is for 5 it is minus 169. 5 is, see, 5 is here. This is 5 value. 5 is here. That is in between 1 and 10, 5 will be here. Okay. For 5 it is 163 minus 163. See, you can see minus 160 here, and minus 163 is in between 160 and 170. So minus 163 will be here. So you can mark all the points up to 10. So you will get a, if you are joining the curve, you will get a curve for the phase plot like this. So phase plot of uncompensated system will be this one, and you can mark each of the points as or name each of the points as a D, E, F, or whatever notation you can use. So now we have two curves, that is, one is this curve, the ABC curve, and other one is this one. These two curves represents the magnitude and phase plot for the uncompensated system. So next, in the graph sheet, what you have to do is, you have to check whether this corresponds to the original design, whether this system satisfies the required condition. See, actually this was the system corresponding to this open loop transfer function, but you have to design it for particular compensation. Okay. So see here, first of all you have to calculate the phase margin corresponding to this system. For phase margin corresponding to the uncompensated systems, again go to the graph. You know that phase margin is obtained at a point gain crossover frequency. See, first of all, what is the gain crossover frequency? For that you have to go to the magnitude plot. So you have to go for zero magnitude. See, zero magnitude means zero gain. That means you have to note the meeting point of this magnitude curve with the zero axis. So at this point its gain should be 0. So corresponding frequency, you can go to downside. Corresponding frequency is gain crossover frequency, that is omega gc. That is notated here, omega gc. So this is the omega gc, that is corresponding to zero gain. And for that omega gc, what will be the value of phase? See, this omega gc will meet the phase curve at this point, right? So you have to note that phase angle value. That phase angle value is, you can see it is minus 167. So first of all, in the case of uncompensated system, you have to go for gain crossover frequency, and you can mark the corresponding phase, that is 5 GC will be equal to minus 167. From that 5 GC you can calculate the phase margin. So 5 GC will be equal to minus 167. From that phase margin gamma will be equal to 180 plus 5 GC. So that will be equal to 13 degrees. That means the phase margin provided by the system is 13 degrees. But your requirement, you are asked to design a system with how much phase margin? Phase margin greater than or equal to 45 degrees. So you have to design a lead compensator for attaining this phase margin. So next step is to designing of the lead compensator. For that, you have to use the procedure that is we have discussed in the previous video. For that, first procedure is that you have to find phi m. Phi m has got an equation. See, before that, phi m equation is gamma d minus gamma plus epsilon, and gamma is obtained from here, that is equal to 13 degree. So 13 degree. Epsilon you can put it as 5 degree in the procedure, and gamma d is the desired phase margin, that is 45 degrees. So you can substitute 45 degree, 13 degree and 5 degree here. So you will get a 37 degree. So you have to design for this case, that is lead compensator for this case. And for that, now you got phi m value. Once you get the phi m value, you can, you know that in the case of a lead compensator, you need alpha and t value to design the transfer function. So alpha value will have the equation alpha equal to 1 minus sin phi m divided by 1 plus sin phi m. That will be equal to 1 minus sin 37 divided by 1 plus sin 37, that is approximately equal to 0.25. Similarly, once you get alpha value, you can find the t value, but you know that here t will be equal to 1 by omega m into root alpha. Alpha value you have, but omega m you don't have. So for finding the omega m value, that has an equation minus 20 log 1 by root alpha. That will be equal to minus 20 into log 1 by root 0.25. That is equal to minus 6 dB. So omega m equal to minus 6 dB. So you can substitute that value here. That is, here we obtain this dB value. You have to convert it into the radians value by taking the anti-logarithm. So omega m will be equal to 5.6 radian per second. So now for this system, omega will be equal to 5.6 radian per second. That is, we can substitute, that is approximately equal to 0.36. So that is approximately equal to 0.36. So the transfer function for the lead compensator will be equal to, in the form of s plus 1 by t by s plus 1 by alpha t, that will be equal to alpha into 1 plus st divided by 1 plus s into alpha t, that is equal to 0.25 into 1 plus, instead of t you can substitute, see, you have the value of t as a 0.36, so you can substitute 0.36. Instead of alpha t, you can substitute the multiplication product of 0.25 and 0.36, that will be equal to 0.09. So you will get the transfer function for the lead compensator. Now you can draw the complete system as using the equation 1 by alpha into this equation, that is this one. 1 by alpha and this will be connected in series to the original transfer function. Okay, so open loop transfer function for the compensated system is obtained by the multiplication of this one. Here 1 by 0.25 is provided in order to eliminate the in order to provide there will be some attenuation. For avoiding that attenuation, we are providing this 1 by alpha here. So to find the complete transfer function for this compensator system, we can multiply all these three. So we will get g0 of s will be equal to 1 by 0.25 into this quantity and this quantity. So you will get the compensator system transfer function as a 15 into 1 plus 0.36 x by s into 1 plus 0.09 s into 1 plus s. Okay. So now you get the transfer function for the compensated system, but you have to verify whether this system is giving the or whether this system is achieving all these cases, that is phase margin is greater than or equal to 45 or and the omega m is less than 7.5, etc. So for that you have to again draw the Bode plot corresponding to this compensated system. This is the compensated system transfer function. You can again draw the Bode plot to verify the design, and for that you know the steps of Bode plot. First you have to draw the magnitude plot, then you have to draw the phase plot. Let us see an overview first of all we have to change the s by j omega, that is shown here. And what is the next step? We have to write the terms of this transfer function in a tabular fashion, and you have to the order will be the increasing order of their corner frequency. Here different terms are 1 plus 0.36 omega, other term is 15 by j omega, other one is 1 by 1 plus j 0.09 omega, and other term is 1 by 1 plus j omega, and the corner frequencies are, for this corner frequency is 1, and for this term corner frequency is 1 by 0.09. For this term the corner frequency is 1 by 0.36. So you have to first calculate the corner frequencies, and you have to write it in the increasing order, and terms should be in the increasing order of their frequencies. So omega c1 is 1 radian, omega c2 is 1 by 0.36 is 2.8, omega c3 is equal to 1 by 0.09, that is equal to 11.1, and here this will be the greatest corner frequency. So this should write at the last term as the last term. So you can see the table. First term will be 15 by j omega, it has no corner frequency, and the last term will be 1 by 1 plus j 0.09 because it has got the largest corner frequency, and other terms are 1 by 1 plus j omega, it has a corner frequency 1, and this term has a greater corner frequency than that of this term. So this is the increasing order of their corner frequency. Next you have to write the slope. For this slope is minus 20, for this quantity slope is minus 20, and for this quantity, see the difference here, the slope will be plus 20 because it is coming in the 1 plus st, it is in the 1 plus st form, that is it is coming at the numerator side, so its slope is plus 20. Next term has got a slope minus 20. Next you can find the change in slope. For finding it, first minus 20 will be added to minus 20, so you will get a minus 40. Next minus 40 will be added to this minus plus 20, so you will get a minus 20. Next minus 20 will be added to this minus 20, so you will get a minus 40. So this is the change in slope finding procedure. Next you have to select a lowest frequency corresponding to lower frequency which is lower than that of the lowest frequency, that is you have to select a frequency less than 1, that is usually you are selecting it as a 0.1, and also you have to select a frequency which is higher than that of highest corner frequency. So here the highest corner frequency is 11.1, so you are selecting 50 radian per second. So lowest frequency you selected is 0.1, highest frequency selected is 50 radian per second. Next you have to calculate magnitude values corresponding to omega, LA, 1 radian, 2.8, 11.1 and 50 radians. So the procedure is same. For first two readings you are using the equation 20 log 15 by j omega, and you can simply substitute for omega. So you will get different gain values like this. And for the next reading you have to find the slope from omega. Here you are using omega c2, so you have to consider the slope from omega c1 to omega c2, and that value is obtained from here, that is minus 40. See, you substitute minus 40 here. Next one is log omega c2 by omega c1. Omega c2 is 2.8, omega c1 is 1, plus gain at omega equal to omega c1, that is 24. Next for omega c3 you have to calculate the slope from omega c2 to omega c3, that is omega c2 to omega c3 slope is equal to minus 20 dB. See, minus 20, see, that is minus 20 dB. So you can substitute minus 20 here, and next you can substitute the value for, next you have to gain at omega equal to omega c2, that is what is obtained in the previous step, that is equal to 6 dB. So in the similar way you can make the substitution and you will get different magnitude values like this. The magnitudes are 44, 24, 6, minus 6 and minus 32. So again you have to plot the magnitude plot on the same semi-logarithmic graph that we have used in the first section. Okay, so here you know that here the positive readings goes up to 44 and the negative readings goes up to minus 32. So after the 0 dB you have to use 3 more divisions. So you can see this is 0 dB, 10, 20, 30 you have to mark here, and by using this you can mark the various. At omega L it is 0.1 correspond to 44 dB. You can mark the point. 1 radian correspond to 24 dB. 2.8 radian corresponds to 6 dB. See here there is no change for this x-axis readings and also for the y-axis readings. You can plot the graph on the same logarithmic graph. Once you plot it, you can find that there is a small difference from this point D. From this point, so the magnitude plot will goes in this manner. That means if starting from here, it will go like this, and then at the point here, it goes to this value, not this value. That means because of the use of the lead compensation, the magnitude plot changed in this way. You can see it from the values, and you have to plot that values. Here one difference is that you will find a difficulty in plotting. Difficulty in finding 2.8. See, 1 radian is exactly marked there. 2.8 radian, there will be little confusion for marking 2.8. See here for 2.8 the gain is 6. Let us see. 2.8. See, this is 1. See, 0.1 to 1. 2.8 will be, see, from this to this is 1, this is 10. So let us go to the upper side. From 1 to this point, 10 is the value. That means 1 to 2 is 1 value, 1, and 2 to 3 is 2, 3, 4, 5 like that. So 2.8 will be somewhere between this 1 and 2. So 2.8 is nearer to this one. Okay, so you can see 2.8 value, this is 1, and up to this point 2 will come. 2.8 2.8 means it will comes between, it will comes between 2 and 3. 2.8 will be, there is, lines are very closely spaced. You can mark somewhere between 2 and 3. You can mark the omega value, that is 2.8. That will be somewhere between here. So for 2.8, you can see this will be nearer to 3. Okay. So that is why I mark this point. They mark this point here as D, that is nearer to 3. 2.8 is nearer to 3, and for that gain will be, what is the gain value? That is, gain value will be 6 dB. So for 2.8 gain value is 6 dB. So you can mark the 6 dB in between 0 and 10. That is why it is going here. So D will be 6 dB. Similarly, you will find a difficulty in marking 11.1 radian per second. For 11.1 radian per second, gain value is minus 6. Where is this 11.1 comes? See, 11.1. See, up to this point it is 10, and after that we are taking, see, this is 100, up to this 100. 1 to 1, it is 100. That means each small division contains 1 to 2, it will be 10. This is 20, this is 30, this is 40, like that. That will be the division. So 11.8 will be, this is 10. So 11.8 will be, this is 21, this is 20, this is 10, and this is 20. So 11.8 will be between, closer to this one. Okay. So, and the dB value will be, see, what is the dB value? dB value will be minus 6. So see, minus 6 is marked here. So it goes for 11.8. So it is nearer to 1. Okay. 1 means this one. Okay. That value is 11.8. Okay. Like that you can mark it here. Similarly, next reading is 50. See, now you can see I have set in the first magnitude plot that here if you are going like a 10, 20, 30, you will not get the 50 value in the graph sheet. So you have to change the scale at this point. That is, this is 10, then this is, it is taken as 100. So you will get a 50 value here. See, this will be the 50 value. So for 50, it is marked as the gain is minus 32 dB. Minus 32 means minus 30 is here. Minus 32 is low, at the lower portion of this 30. Like that here it is 10, and 50 is, look at the lowest portion and the upper portion. This is, here will be 50. Okay. So like that the graph reading. Similarly, now you get the phase magnitude plot for the compensated system. You can mark, see, magnitude plot for the compensated system will go like this: A to B, then to D, then to E, then to F. So next we have to draw the phase plot. Similarly, we can draw the phase plot. For that we have to take the phase equation. Here the phase equation is different. See, the compensated system will have this function, and what will be the phase equation? First of all, at the numerator 0.36 omega, that is tan inverse 0.36 omega is one term, that is at the numerator, so it will be positive. Next term is j omega, and its phase will be minus 90 degrees since it is coming at the denominator side. And the next term is this one, and it will be minus tan inverse 0.09 omega since it is at the denominator side. Next term phase will be minus 90 degree. So there are two minus 90 degree terms. So sorry, this is minus tan inverse omega. So altogether we will get the phase equation as a tan inverse 0.36 omega minus 90 minus tan inverse 0.09 omega minus tan inverse omega. So instead of omega, you can substitute different values. Here we use, see, here we use 0.1, 1, 2.8, 11.1 and 50 radians. And for drawing the phase plot, there is no need to take this 2.8 and 11.1 because it will be very difficult to mark it on the graph sheet. You can use different values, 0.1, 1, 5, 10, etc. like that. Or either you can use 2.8, whatever value you can take in between this 0.1 and 10. So here it is used as a 0.1, 0.5, 1, 2, 5, 10. It is chosen these values for simplicity, okay. you can easily mark it on the graph sheet. That is why it is omega values are taken like this. You can either go for 2.8 value, 11.8 or whatever it is. So for that values, the corresponding phase values will be like this one. And you can plot this phase value on the graph sheet. See. So you will get 0.1 is minus 94. See, here phase plot is also drawn on this same graph sheet. 0.1 is this minus 94. See, here is 90, minus 94 is in between these two. So minus 94 will be here. And next value for 0.5, it is minus 109. Next 0.5, see, this is 0.1 and this is 1. Therefore 0.5 will be here. This is 1, this is 0.1, this is 0.2, 0.3, 0.4, 0.5 will be here, 0.5 will be here. And for 0.5, what is the value? It is minus 109. That is, this value will be in between minus 10 and 20. So this is the value. And the next one is 1. For 1, what is the phase value? Phase value is minus 120. Minus 120 is here. Minus 120 is here. And that 120 corresponds to 1. So 1 is here. This is the 1. And the next value is 2 for 2. See here in the graph, 2 is not marked, but here 1 and 10 are marked. So go to the upper scale, that is 1 and 10 are marked between. So this is 1, this will be 2, 3, 4, 5 like that. So 2 will be here. That is for 2. What is the value? Minus 128. Minus 128 is in between. Minus 128 means somewhere between 120 and 130, and go for 2. That 2 value will be here. So you can mark. Similarly, you can go for other values and you can mark the graph sheet, and you can join the phase plot by joining the points like this. So you will get the graph like this. So this is the graph phase plot for the compensated system in the case of lead compensated and control system. So now you get different graphs. Next you have to calculate corresponding phase margin. For that you have to find the gain crossover frequency from the magnitude plot. See, this was the compensated magnitude plot. See, this is a compensated graph, and you can see it meets the 0 dB axis here. So now you look at the compensated magnitude plot. This is the compensated magnitude plot, and that plot meet the 0 dB axis at this point. See, and that point correspond to the frequency. See, this will be the frequency, that is omega m. You can mark it as omega m. That frequency is omega m, and that you have to note it from the graph sheet. This is moreover corresponding to, this is 5 or above 5. So that value will be equal to, it is approximately 5.6. You cannot say that it is exactly 5, because it may be somewhat greater than 5. So you can say 5.6. Here it is given as 5.6 or somewhere above 5. So that frequency correspond to 5.6, and corresponding 5.6 meets the phase plot here, and corresponding phase angle will be minus 134 degree. So you will get, see, phi GCO will be equal to minus 134. Once you get phi GCO value, you can calculate phi gamma 0, that is phase margin, as 180 plus minus 134, that will be equal to 46. So you can conclude that actually what we have gone through all this magnitude and phase plot procedure for verifying that the given designed system is satisfying the phase margin 36. Sorry, phase margin greater than, what was greater than 45 degree. Phase margin is greater than or equal to 45 degree. So here you got the value as a minus 1. What was the value result? Let us see. It is 46. That means it is greater than 45. So the designed lead compensator exactly meet the specification. That you can say also here omega GCM value, or here omega value is 5.6 and that is less than 7.5, which is that is also, that requirement is also satisfied here. So the given or designed lead compensation satisfies the requirements. So the phase margin of the compensated system is satisfactory and the design is acceptable. And you can write the result as a transfer function for the compensated network is this one. And also you can write the open loop transfer function, and closed loop transfer function will be like this. So that's all about this problem. If you have any doubt, you can ask.